In Physics 10 right here, we want to look at a new subject right here, and this is what we're going to call electrostatics right here. Now, you notice when we already went through properties of particles, one of the properties was the mass right here, measured in kilograms. And we said masses attract each other. We called that the gravitational force. That was back first section right here, where we said that big G was this very small number right here. Well, it just so happens that there's another property of particles that governs a different force. We don't call it mass, we call it some other property of the particles. We call it charge right here. And the units are not kilograms, they're called coulombs right here. And this property also gives you a force, and the force, we call this the electrical force, and this electrical force looks exactly like the gravitational force, except instead of masses, you have the charge instead of the mass. And it still depends on the distance squared. It's a three-dimensional, remember we said it was distance squared because of 3 dimensions of space. And this constant dictates the strength of that force. Well, this constant is around 10 to the plus 10. You notice that was 10 to the minus 11. This is infinitely greater than this right here. Even though we notice this one all the time, we don't notice this. The reason why we don't notice this, even though it's infinitely, when I say infinitely, I mean it's like comparing these two is like comparing a grain of sand with the earth. That's the difference in strength right there. It's because this one comes in 2 flavors. There's only 1 flavor of mass, there's 2 flavors of charge, and we give them the name plus and minus right here. And so anytime you have 2 of the same charges, 2 pluses, they repel, or 2 minuses, they repel, but opposites attract right here. Which means, and since matter is mostly neutral right here, we're infinitely attracted to everyone else, and at the same time we're infinitely repulsed by everyone else, and the two just balance out and we don't feel that force right here. We should also say that these charges are conserved. You can't create a net charge and you can't destroy a net charge right here. Okay, so now it's this force that holds us together. It holds atoms together. If we look at an atom, what do we got? We got like a nucleus right here. We got these electrons that are going around it. The electrons are the minus charge. And the positive charges are the rest of the atom that lost an electron. It's not just the proton, it's just the rest of the atom. We call it a positive ion right here. And since the electrons, the mass, is so much smaller than the mass of the plus charges, and if you push equally on them, the minus is going to do all the moving. Plus charges never move, it's always the minus charges. If we look at this atom right here, like uranium is 92-238 on the periodic table. The 92 means the number of protons, but that's also the number of electrons because the atoms are neutral right here. The other number right here, this 238, if you subtract these two, that gave you the number of neutrons right here, so it would be 146. So uranium would have 146 neutrons, 92 electrons, and 92 protons right here. Now, if I wanted to make this a charged atom, I would knock off one of the outer electrons right there. We can knock off these outer electrons off of atoms by, say, walking on your carpet right here. Your carpet, and say with your rubber shoes right here, you're scuffing electrons off the carpet onto your shoe right here. And they don't want to just stay in your shoe, they're going to just kind of go all over your body right here. And anytime you separate a charge, we call that a voltage. So voltage is just a separation of charge. Here I have a battery right here. There's this little AA battery right here. There's a chemical reaction in here that separates the plus to this side with a little bump on it and the minus to that side right here. And the voltage for this battery is 1.5 volts. That means for every coulomb of charge that when I connect these pluses would like to get to the minus. If I put a way for these to come back over to here, I'd get 1.5 joules of energy for every unit of charge right here. It's similar to if I pulled this away from the Earth right here, and then I let it go, what would it do? It would snap back to the Earth and I'd get energy out of it. That's exactly what we're doing here with this battery right here. We're just separating the charge. And that's what you're creating right here when you just don't lift up your feet. And you probably notice it if you ever go touch the doorknob handle, it's going to discharge you right there. Okay. So that's one way you can move around charge. We usually call that by friction right here. Right? Now, different materials can move charges differently right here. If we have a piece of steel or even say copper right here, for every copper atom, pretty much the outer electron is pretty much free to go and do what he wants. So you got all these free electrons. There's a lot of atoms, so you got a lot of free charges. And if I put some plus charge over or minus charge over here, I can push these charges along right here. And we'll see later, we get a current right there. So this would be considered a good conductor right here. If you got a lot of charges that can move around right there, we call that a good conductor. It would also be a good conductor of heat, but usually if you're a good conductor of heat, you're a good conductor of electricity. If I have a piece of rubber here, the charges are actually frozen in there, and so they don't transmit, they can't move around right here. They're kind of locked in place, and we call that an insulator right here. So we've got materials that's either a conductor or insulator. We can also bring up something called the superconductor. If you were to take this piece of copper and get it really cold, that is down to 1 or 2 degrees Kelvin, then this thing right here, these charges would move it'd be like no friction. And so we call that a superconductor right here. And so there would be nothing to slow. Once you get the charges moving, they just keep moving forever. It'd be like a frictionless surface right here. We call that a superconductor. Now, there is no such thing as a super insulator right there, because once you don't move them, that's it right there. But there is something that's halfway in between a conductor and an insulator. We call that a semiconductor. Now, if we look at usually they make them out of silicon. If we look at silicon atom, I don't have a periodic table over here, but the silicon is the 4th one over on the periodic table, which means there are 4 electrons in the last shell. And really, that's all that matters in atoms. What they do is just the amount of electrons in the last shell. It's got 4. It'd love to have 8. But they seem to share. Here you got this crystal of silicon. You notice he's got 2, 4, 6, 8. This guy is a happy atom. He's not going to give up any of his electrons, right? They're frozen in there good. This is a good insulator right here. But suppose I were to take something that had 5 electrons in the outside shell, like phosphorus. Phosphorus, which is what? P on the periodic table. If I were to sprinkle a little bit of P on this, this thing would have 5 electrons. It would have the 4 to share and the extra one right here. You notice right here, this extra one can now move around. It makes it a little more conductive. If I were to sprinkle a lot of phosphorus on here, I could make this a better conductor. So I could vary it. They call it doping it right here. And we call this an N-type superconductor, an N-type semiconductor, because that's a negative charge, N meaning negative charge right there. So I can vary, I can make it real conductive by putting a lot of this on, or I can make it more insulative by hardly putting any on right here. Now there's another type of semiconductor, and that is something called the P-type. If I didn't pick one with 5 electrons, if I picked one with only 3 electrons in the last shell, something like boron, maybe I'll put that in green. Boron has 3 electrons in the last shell. Well, there's 1, 2, 3. It would love to have one right there. Right there. It's yearning for one right there. It's got a we could call it a hole. He's waiting for one. He wants one so badly that he'll steal one from his neighbors. So if he steals this one and this goes over here, then you notice this hole came up to here. And then he steals one, and then that hole will go somewhere else. And so now what do you got moving around here? You got these holes moving around. And a hole is like a positive charge because it's not a negative right here. So we call it a p-type. It acts like that right here. So there's two types of semiconductors, with electrons or with little holes right there that would love to have an electron right here. So what can we make with these two types of semiconductor? Well, if we get a blob of this type, and we get a blob of that type, and we stick them together, stick them and put a wire and connect it up to a battery like this right here. You notice the N-type has electrons. These ones got holes right here. Now, these electrons don't know these holes are there because this distance is huge compared to the size of the atom. Otherwise, they would just go fill in, but they don't, right? This is a long ways away. So, but if I put this battery just like this, right here, with the bump over there, and that's the plus, and this is the minus is charges here. Remember, minuses repel. It would push these this way, and we would get charges to flow around here. Charges would flow. If we turned the battery around and hooked it up this way, right here, then this side is plus. These electrons would just come over here, the holes would come over there, and you wouldn't get any movement of charge. It would just stop right here. And so we call this object a diode right here. And what does a diode do? It only allows current to go one way. If you hook up the battery one way, charge will flow. If you hook it up the other way, charge won't flow. It's like a one-way valve right here. And we can even make certain types of ones that when the charges do flow, they light up. We call that an LED right here. You see a lot of light-emitting diodes right there. Solar cells, they're just this right here. This is all a solar cell is, just a diode right here. Now, if we take and make a sandwich out of these two pieces, that is, we take, let's say, two of these and use these as the bread, and this is the meat right here, put it in between, right there. You make a sandwich, you stick a wire there, and a wire there, and you got the biggest invention in the history of mankind besides fire and the wheel. This is like number 3. It's the transistor right here. Well, what does this do? This is like, it's like a pipe. Think of this as like a water pipe, and this is the valve right here. So if you put a little bit of a voltage there, it opens up this gate and charge can flow, or you can turn it down and turn it up. That's all this thing does right here. And so if you look in all computers, they're just switches. On, off, on. That's one thing. This thing can do a lot more than just switch, but one of the things this can do is it's like your faucet in your bathroom. You can either turn it on, turn it off, turn it on, turn it off. That's all computers do, is just switch right here. So you can do a lot of other things besides that. So this is the transistors, and so this is just on charges right here. Electrostatics means charges are not moving. We're really talking about at rest, right?